Okay, welcome back, everyone. Hopefully your Thanksgiving break was, enjoyable in some way. A couple of things. One, I'd gotten a few emails in the last couple of days asking about the MATLAB format. I spelled this out, if not directly. I can't remember if I actually included it on the header of when I posted the MATLAB projects or not, but I thought I did, but it's possible that I didn't. But I'm pretty sure at least I put it in an announcement. Basically, the format should be published in file, not like the raw M file, because you don't get any of the pictures. Also, so it should be published to PDF. The default option, I believe, usually in MATLAB is published as HTML. The problem with that is that a lot of times it breaks the images. So publish to PDF should be the thing that you do. If you're confused by that, the TAs can help. Also, I'll post another just reminder announcement of what to do. I'll even maybe take a quick like screen grab of where to go in MATLAB to change that option. But I mean, if you just Google like publish M file as PDF, that should be good enough. Anyway, so yeah, published PDF. That's how it should be uploaded. So yeah, just do that before tonight. So if you've already uploaded it in a format that's not that, then you still have plenty of time. You still got like like 12 hours to upload it. So anyway, and that's how all the MATLAB. That's how anything you hand in MATLAB is going to be exactly in that format. So anyway, as I was saying in chat, your last MATLAB project is going to be posted later today. I'll send out an Elms announcement when I do, and it'll be due on the last day of classes. So it'll be a couple weeks from today. So it'll be due at like midnight, 2 weeks from today. Same rules. You don't have to keep the exact same groups, but still no cross section groups. Same groups the same size, and same format restrictions as before. So I'll add that column later. But anyway, so that's the deal. And then there'll be no more MATLABs. That will be that. So anyway, last time we were covering symmetric matrices, and the primary thing that we used our discussion of symmetric matrices to do was this spectral decomposition, which we saw was actually really nice. But anyway, that's not the only purpose of symmetric matrices for us. So something that is very, very nice application of symmetric matrices comes in the definition of what are called quadratic forms. So this might seem a little like off key at first, because we've spent the entirety, except for like one or two exceptions, we spent the entirety of this course talking about linear equations with very few exceptions. But quadratic forms necessarily involve some nonlinearity, as you'll see. And so a quadratic form, on Rn is a function called Q. That's a function Q defined on Rn whose value at a vector x can be computed via an expression of the form I'll write it on the next line. Q of x is x transpose A times x, where A is a symmetric matrix. Okay. And so here's where our symmetric matrices make an appearance. Okay. So a quadratic form is something that looks like this. Okay. This A is called the matrix of the quadratic form. So A is called matrix of the quadratic form. Okay, so what are some examples of this? Why should we care about quadratic forms? Well, it's kind of like a really easy symmetric matrix that that I can come up with here. Well, what about when I use something really nice like the identity? Right? So if we use something really nice like the identity, then what does this quadratic form involving the identity, which is definitely a symmetric matrix, what does this become? This is X transpose X, right? What is this? Right? You've seen how this is before, right? What is this? This is just, if I wrote this out, right? Let's say I'm using standard notation here. What is this? This is my entries, x1 squared, x2 squared, and so on, right? This is actually my sum of entries in this way. This is just the length of the vector x squared. Okay. In fact, before when I was saying that, this is going to involve nonlinear expressions, this was exactly the exception I was thinking of that we'd seen earlier in the course. That's a nonlinear expression, right? This is kind of like the one thing that we'd seen, other than some, I think on one of the exams I'd asked you for an example of a transformation that sent 0 to 0 but wasn't linear, right? So you could come up with something that involved nonlinear terms like this, but apart from that, everything else is dealt with linear equations. So this is kind of a first for us to deal with something like this, except in this example. But hey, right, this we can view a quadratic form Q defined in this way to be related to length of vector, and we know how important that is. So this is pretty important, just from this immediate association with viewing the square of the length of a vector in this way. Okay, now, more generally, of course, quadratic forms have applications in all over the place, not just in math, but in physics and other things in applied math like signal processing. And even off the top of my head, in geometry, you can think of curvature in terms of quadratic form. So certain aspects of curvature you can think of in terms of quadratic form. So there's tons of application of quadratic forms. We're not going to touch on all of them. No way. We don't have enough time for that. But that's quadratic forms are very, very useful. Okay, so let's see some more examples. So let's pick some symmetric matrices to look at here. So here's one. All right, let's just pick a diagonal matrix. All right, so diagonal matrix is kind of a really, really nice example of symmetric matrix. So if I use a diagonal matrix A, what is the associated quadratic form that has A as its matrix? Well, this takes vector x. The A here is, so if I'm writing it, if I transpose my vector x, so this is x1, x2, written as rho, times matrix 4, 0, 0, 3, times column x1, x2. So what is this if I actually do this multiplication? This is going to be 4x1 squared, right, plus 3x2 squared. And my other terms are going to be zeroed out by these zeros in my matrix, right? So if I was actually going through this step by step, so let's do this multiplication. So this would be 4x sub 1 times, or plus 0 times x sub 2. Okay, and then this would be 0 times x sub 1 plus 3x sub 2. So I have column vector that's 4x sub 1, 3x sub 2, and then I'm multiplying x1, x2 by that column vector. So I get 4x sub 1 times x sub 1, so 4x sub 1 squared, plus 3x sub 2 times x sub 2, so 3x sub 2 squared. So I get no cross terms when I use a diagonal matrix here. Okay, so I'm drawing attention. It seems like a very obvious thing, but I'm drawing attention to that because we one of the first things that we're going to do with these quadratic forms is try to eliminate these cross terms, and you'll see how we go about that in a second. So note no cross terms, okay, because of these zeros. All right. So then let's pick an example of one that actually has cross terms. So again, I'm restricted. If I want to talk about quadratic forms, the matrix I pick has to be symmetric. So let's do another example. Let the matrix quadratic form be 3 minus 2 minus 2, 7. Okay. Then what would the associated quadratic form be? Well, just do this multiplication. So this is x of 1, x of 2 times matrix I've written here times column containing x of 1 and x of 2. So let's just do this multiplication. So so I'll do it on the right here. So this is x of 1, x of 2 times a column vector. That column vector is 3 x of 1 minus x of 2 in the first entry. And in the second entry, this would be minus 2 x of 1 plus 7 x of 2. Right? Okay. So then multiplying this out to see what I get here, I would get x of 1 times the first entry. So x of 1 times 3x of 1 minus 2x of 2 plus x of 2 times that second entry minus 2x of 1 plus 7x of 2. And so just expanding this, this is 3x of 1 squared minus 2x of 1 x of 2. Here I would have minus 2x of 1 x of 2 plus 7 x of 2 squared. And so simplifying this, this would be 3x of 1 squared minus 4 x of 1 x of 2 plus 7 x of 2 squared. Okay. All right. Emmett asks, when is the final? So our final is, off the top of my head, I can't remember exactly the date that the final is scheduled for, but that will be the due date of your, actually. So I will look at when it is, and so I will determine based on when it is whether I will make that the due date or the beginning date. But I will basically I will post your final exam within some X number of hours of that day, and you will have at least 24 hours to access to this. Okay, so time frame will be slightly less than, say, your first exam. So that is the plan. But I'll actually include that in my announcement later today, since it's coming up in a couple weeks. Okay. So this is my result. So obviously there is in fact a cross term here, which is not ideal for a number of reasons. And we seek to try to eliminate this cross term if possible. Now, how would I go about trying to eliminate this cross term? Well, so it turns out that my approach here is to think of changing variables. And so through a change of variables, we'll see how we can eliminate this cross term and what that does to our quadratic form. So actually, there's really nice geometric picture that goes along with this. So before I do that, let's say that you are here in all three of the examples we just did. We started with the matrix and computed the quadratic form like that, but we saw that all these quadratic forms, say in the case of 2x2 matrices, they all look like this, right? It's something like this, okay? And so what if we're actually given this instead of the matrix? Can we compute the value of the quadratic form, from this in the same way? Well, yeah, this is just as good as being given the matrix almost, in a sense, because I can actually just compute, I can compute this directly from the entries of my vector. So here's another example, right? Suppose that I'm actually given a quadratic form, and I'm told that it's a quadratic form, right? So here's the thing is that, if I write out some generic function of, say, 2 or 3 or however many variables and ask you whether or not it's a quadratic form or can be thought of as a quadratic form, well, that's a different sort of question. But let's say that I give you this thing and I tell you, and you believe me, this is a quadratic form. I want to compute, compute qx or q of x for the vectors, say, -3, 1, and let's do one more. Let's say 2, -2, and just to do a couple. All right. And so if I compute, say, q of -3, 1, well, I can just view this as a function of 2 variables, or my x of 1 variable is -3, x of 2 variable is 1, and I just plug this in, right? This is like a Calc 3 question. So this is -3 squared minus 8 times -3 times 1 minus 5 times 1 squared. Okay, so let's see, 9 minus minus 24 minus 5, so that's 28. Okay, similarly, if I wanted to compute, 2 minus 2 here, this is 2 squared minus 8 times 2 times -2 minus 5 times -2 squared, which is 16. Okay. Now, you might. The thing is, it might seem like a strange thing to care too much about the cross terms here, when computing these things is not too bad. But conceptually, it's nicer when the quadratic form in question doesn't have these cross terms, and so the idea is to try to eliminate these things. Now, I already spilled the beans a little bit and said, we're going to use change of variable to do this. So our idea is we wish to eliminate the cross terms in some given quadratic form q of x. To do this, we seek a change of variables. Now, this is really going to showcase where the fact that the matrix A is symmetric comes in. Okay, because if A weren't symmetric, then trying to do this is going to be a nightmare here. Let's see. So, question in the chat. Yekta asks, do we need one MATLAB turn-in per group? Yeah. So, just one MATLAB turn-in per group. That's all you need. In fact, specifically, do not turn in more than one per group, because this will make it easier for the TAs when they're going through these. If you, when they download all your submissions, if like everybody in the group has submitted them, then that vastly multiplies the number they have to go through, and then they're going through a bunch of stuff that they've already actually assigned grades for that group, right? So it's just a huge waste of time. So I will also include that in the announcement again. Yeah, I got a few emails about that, but it's one MATLAB turn-in per group. You only need to turn in one. So yeah, that's good. I'm glad that was brought up. Okay. Now, in order to do this, just a normal change of variables, right, would be so what we call a change of variables, right? So if x is like a vector of, say, variables in Rn. A change of variables, right? So quick definition, just to remind you of a change of variables. So a change of variables, since we want to be able to go back and forth, the idea is to come up with an invertible matrix P such that X is Py, right? Or if you want to view it going in the other direction, Y is P inverse X. So P is an invertible matrix. So if you take an invertible matrix and you form either X is equal to Py or Y is equal to P inverse X, then what you've done is you've changed variables between X and Y. And of course, the way of viewing this and the way that we did it earlier in the class is that you went from, say, standard basis in Rn to the basis of Rn given by the columns of P, right? If P is invertible, then columns of P form a basis of Rn, and so that's what you've done. It's a change of basis where you went from standard basis to basis given by columns of P. Okay, so that's the idea here. Now, to make this really nice, or maybe I should write out first why I would want this to be nice in the first place. So suppose we make a change of variable. Let's make a change of variable in our quadratic form Q of X. So this is, remember, this is X transpose AX. So let's make a change of variables here. Then X transpose AX is going to become PY transpose A times PY. Okay, which becomes, remember, when you transpose product, it reverses the order. So this becomes Y transpose P transpose A P Y. Okay, so rewriting this, right, as matrix here, this is P transpose AP is the thing. So the difference, once I've swapped out the X's with Y's, this A gets mapped to P transpose AP. Okay, so now that you have seen this, right, this is the hint of what you should do. Okay, and so I'll ask, and you can post in the chat if you notice what it is you should do here based on what we did last lecture. What is it that I want this matrix to be, right? This is the hint for what you should, or rather why you can do this. So what do I want this matrix to be? Remember, I want to eliminate the cross terms. Well, going back to our examples, we had an example of a quadratic form that had no cross terms. So there it is, right? This one had no cross terms. And the matrix in question was a diagonal symmetric matrix. Of course, in our other example, we had a matrix that's not diagonal, but still symmetric. So we still have quadratic form here, but we got cross terms. So, right, I'm definitely like trying to pull it out of you here. The point is that I can actually look at this and say what I want this matrix to be is diagonal, right? But the second I say that, right, what do you get from this this expression? When the second I say that I want this to be diagonal, or maybe even just the second you see an expression like this, the first time we brought up an expression like this was for a particular type of matrix, which was, it's an orthogonal matrix, right? It's, yeah, right. So you're diagonalizing a matrix. That's right. Okay, so you're diagonalizing a matrix, but you're diagonalizing a matrix in a special way. No, P's not a, I mean, P is a matrix. So P is a matrix, but this matrix P is of a special form if A is nice enough. And maybe that sounds a little vague, like I'm not really saying anything, but So we want a diagonalization here. Yeah, we want that to be diagonal. So we're diagonalizing A. But we're diagonalizing A with a matrix that is nicer than just a general invertible matrix. Yeah, right. So Gustavo said it in chat. So this is an orthogonal matrix A. And so what we want is a matrix that is orthogonally diagonalizable, but that's a symmetric matrix, right? So of course, since A is symmetric, it is orthogonally diagonalizable, i.e., there exists a diagonal, or I should say, an orthogonal matrix P such that A is equal to P D P transpose with D diagonal. And if this slightly confuses you, remember that if P is orthogonal, then P inverse is P transpose, right? So if you have a matrix, even if it's not square, right? If you have a matrix that has orthonormal columns, then when you multiply in the way that this works, so when you multiply by its transpose, you get the identity. Okay, and so that's the you either get the m by m identity or the n by n identity. But that's true just with orthonormal columns. So if it's orthogonal, right, it's square. And so we have a square matrix. Its inverse is P transpose, or its inverse is its transpose, I should say. And so when we write something like this means, of course, another way of writing this is that P transpose A times P is equal to D, right? And so the end of this, right, the resulting thing we get out of this long line of equalities is that a change of variables takes us from X transpose AX, this goes to Y transpose DY. Okay, where D is the diagonal matrix you get from this diagonalization process. And because A is symmetric, this is always going to be nice. It's always orthogonally diagonalizable. Okay. And so, to see how this goes, let's refer back to this past example. So the last example I did where I actually didn't write out the matrix, we just started with this version of the quadratic form. So here's my quadratic form Q. So the previous Q actually has an associated matrix. So let's say previous example involved the quadratic form. Let me just copy it here. That'd be more convenient than always bringing that thing back. So this is x1 squared minus 8 x1 x2 minus 5x sub 2 squared. Okay, so this is the previous example. This actually has matrix A given as 1 minus 4 minus 4 minus 5. Okay. Starting here and coming up with the matrix, if you know it's a quadratic form, you might already see how to do this. Actually, I'm not even going to say anything else about it. You definitely see how to go from here to here. Anyway, so this has the matrix given here. So then it definitely is it has a cross term, right? Minus 8 x1 x2. So let's try to get rid of that through orthogonally diagonalizing this and changing variables. So A has eigenvalues. Or I'm just going to go ahead and write the eigenpairs, so because we're not actually going to compute these. You think you've had enough of eigenvalues and eigenvectors to last you a while. So this has eigenpairs 3, and I'm going to go ahead and normalize the eigenvectors so that they're unit. So this is 2 over root 5 and minus 1 over root 5. So that's our first eigenpair. Second eigenpair is minus 7, and the associated normalized eigenvector is 1 over root 5 and 2 over root 5. Okay. All right. Now you might notice that these eigenvectors are automatically orthogonal. So note that eigenvectors are automatically orthogonal. Why? So the reason I'm saying automatically here is that I don't even have to compute. You can if you want to. You can just look at them and see. They're orthogonal, but they're automatically orthogonal. They're guaranteed to be. Because A is symmetric, and so one of the things about A being orthogonally diagonalizable is that the eigenvectors from different eigenspaces automatically are orthogonal to one another. Okay, so that's one thing that you get immediately out of this. So anyway, the P matrix in question, if I let P be the matrix whose columns are these two eigenvectors, so this is 2 over root 5 minus 1 over root 5 and 1 over root 5, 2 over root 5. So if this is my P, my matrix D, of course, is the one containing the eigenvalues in the right order, so this would be 3, 0, 0, minus 7. Okay, then A is, of course, PD, P inverse, which I can write as PD, P transpose. So D is P transpose AP. You could check all those if you really wanted to, but we know that this is the case because we've done everything correctly here. Okay. And so if we use the change of variable determined by P, right? So if we replace X with Py in our Q of X, where, I'm using the notation, so X is the vector X1, X2, and Y is the vector Y1, Y2, then this expression that I have here at the top, just reminding you, I'm going to write this again. So this is x sub 1 squared minus 8 x sub 1 x sub 2 minus 5 x sub 2 squared. This is how I express this quadratic form x transpose ax. But of course, using this thing that I did in the run-up to this example, right after my definition of change of variable, this computation here, where when I've swapped x with py, ultimately what I get is y transpose dy, right, which is p transpose a p, but that's diagonal. That's this diagonal matrix D here. And so what I get is that this is y transpose dy, right, using that change of variables here. But this is easy to compute because D is diagonal. What is y transpose dy? Well, this is 3 y1 squared minus 7 y2 squared. And so I have changed from a quadratic form of x to another variable, but I went from a quadratic form that has a cross term, right, to one that doesn't. Now, the variables I'm using are different, but this is a string of equalities, right? And so these things have to be the same. And what that means is that now I'm dealing with I can basically start here with a quadratic form that has cross term, but I can actually eliminate it. I just have to use different variables, right? I've relabeled these variables as something else, and this might be a little tricky when you think about what you've done here, right? Because the fact that there's equalities here means that you haven't really changed anything. And so then what are you doing when you do this process? So I'm going to state a theorem, and then I'm going to show you some pictures that show exactly what's going on here, and also help explain the name of the theorem. Okay, and so what we did here, and actually what we did essentially right before this example, was a proof of this theorem. What we proved is the principal axes theorem. So what is the principal axes theorem? Oh, a little bit off the page. Yeah, so Gustavo, you have to normalize. So the reason that you have to normalize is because all of the facts that you want from all the facts you want to be true, like the fact that you can replace the inverse with the transpose, that if you don't have them normalized, then when you multiply matrices that, like if you take a matrix, right? And I know this is a little bit confusing because the name of the matrix is called orthogonal, but it has orthonormal columns, and that's important. Because if the columns aren't orthonormal, then the issue is when you multiply the matrix by its transpose, the entries on the diagonal aren't all going to be 1, right? Those entries on the diagonal all need to be 1, because when you take the matrix and multiply by its transpose, what you're supposed to get is the identity, right? And so all those diagonal entries have to be 1, right? And 0 everywhere else. So you get the zeros everywhere else still, right? Because that comes from orthogonality. Right, so orthogonality gives you the zeros everywhere else. You still get a diagonal matrix, but you don't get the identity, right? And that's what you want. So to say that you get the identity, you need those to be normalized. They have to be unit vectors. Okay, so that's why you have to normalize. So you just have to get it in your head, like orthogonal matrices have orthonormal columns. Okay, but remember, as I said when we were doing Gram-Schmidt, like the normalization part, that's the easy part. It's coming up with the orthogonal set of vectors that's the issue. If you already have an orthogonal set of vectors, then making it orthonormals is trivial. You're just scaling them all by their length. Okay, so what's the principal axes theorem? So let A, which is an n by n matrix, be symmetric. Okay, then there is an orthogonal change of variable x equals py, where what we mean by that is P is an orthogonal matrix that transforms the quadratic form x transpose AX to y transpose dy with D diagonal. i.e., no cross term. Okay. All right. So, like I said, the proof of this is we actually already did it. Now, where does the name come from? The columns, it's a quick definition, the columns of P are called the principal axes of the quadratic form that we started with. Okay. All right. But what does this mean? Why am I calling them axes in the first place? What is actually going on here? The best way to see what is going on is to look at the following. So geometrically, to see what's going on, we consider looking at the following expressions. So we consider looking at the equations that look like x transpose ax equals c for c a constant. Okay. Now, what do those look like for a quadratic form? What do equations like this look like? So these are say points, right? My x is in R2 in this case. We're looking in the plane because we want our pictures to be nice. So we want to be, have a hope of drawing this. So if we take vectors in R2, we look at equations like this. What sorts of things can we get, right? Well, I mean, we're assuming this is a quadratic form, so I don't have to write out stuff like A is symmetric and all that. So this is a quadratic form. What do I get? Well, you might imagine there's some easy stuff I could get, right? So like I could get right, like x sub 1 squared plus, well, here, maybe I'll just write out some stuff I could get here, right? I could get x sub 1 squared plus x sub 2 squared is equal to 9, right? That's something. If I choose c to be 9 and I have the easiest possible quadratic form, where I've picked a to be the identity, then this is what I get. Okay, but what is this the equation of? Well, that's the equation of a circle of radius 3 centered at the origin. Of course, this is a really, really special case, right? I'm not going to get this typically. So what about I get something like this? Yeah, I could get something like that, right? X sub 1 squared plus 3x sub 2 squared is equal to 4. So that's something else I could get. So this isn't going to be a circle anymore, but it's going to be an ellipse, right? This is going to be an ellipse. Of course, I could also get something like, I could get something like, say, x sub 1 squared minus x sub 2 squared is equal to 1, right? What is that, right? So these are both, a circle is an ellipse, so ellipse is a possibility, right? Okay, what about in this case? What do I get? Well, in this case, I get a hyperbola, right? What are some other things that I can get? I can get two intersecting lines. You can think about how that works. Yeah, right, Gustavo. So ellipses and hyperbola is what you get. So two intersecting lines, that's something I can get. You can think about how you would do that. You can get a single point, or you get something that contains no points, right? You get something there's just no solution here. And here's a very easy example here. What if I'd chosen, I just said let c be a constant. What if I'd let c be like minus 5, right? If c is minus 5, and on the left-hand side my quadratic form is x1 squared plus x2 squared, no way can that equal minus 5, so you get no points in that case. All right. Okay. So there's some options here, right? I'm going to focus on ellipses and hyperbolas just because it's a really nice image to see how this works. So why did I bring these up in the first place? The idea is to see what it is that happens. Now, if A is diagonal, all right, these things, I know I don't have it written on the page, but I said it in words, right? So maybe I'll just do it again because I don't like writing something here that makes it seem like these are the only two. Plus other stuff, right? Other stuff possibilities are things that we can get, okay? But I want to focus on ellipses and hyperbolas just because the picture is nice and it shows exactly what's happening. So if A is diagonal, the boxed things at the left here are in standard position. Well, what does that mean? It means they're oriented in the way that you think of them if I ask you to draw these things. So for instance, let me refocus the camera here. Okay, so there's our camera. So this is an ellipse in standard position, and this is a hyperbola in standard position. Okay, so here's some generic equations that give you these things. All right. So if you have a diagonal matrix defining this this quadratic form, then they're in standard position. This is how they start out. But let's say that you're in the more general case that A is not a diagonal matrix. Okay, then what you have are pictures that look like this. So if A is not diagonal, then what happens is that these things you started with have been rotated out of standard position. Okay, so here's what they look like. And as is labeled on these pictures, what is it that you're doing when you take an ellipse that, here's the equation in the quadratic form writing for this ellipse and this hyperbola. Okay, what are you doing when you take a hyperbola like this and you find the change of variable that turns this into something that has no cross term? You are finding the axes y sub 1 and y sub 2, right, that are oriented in such a way, or that are configured in such a way that this picture is in standard position with respect to those axes. That's why they're called the principal axes. Okay, they are these axes, these things that come from the columns of P, for which if you turn your picture, right, now it is in standard position relative to those axes. Right, same thing here if I'm looking at the hyperbola, right, and I rotate my picture a little bit. Oh, look, now it's in standard position relative to y sub 1 and y sub 2. What that's saying is that if I change variables, if I go from x sub 1 axis to y sub 1 and x sub 2 to y sub 2, now if I were to write out the quadratic form in these new variables, y sub 1 and y sub 2, it would be diagonal. Right, but we know that, right? That's exactly what we did. But this is geometrically what it is that's going on. Okay. All right. And yeah, so as Gustavo said, you're making the principal axes your new reference axes. So that thing I was doing with the textbook where I was rotating it around, like that's essentially me turning my head. That's showing what I'm doing when I'm changing the variables, right? So I'm essentially taking that picture and rotating it in such a way that now it's in standard position. Okay. All right. So that's what's going on. All right, so a couple more minutes I just want to give some quick definitions that will allow us to talk about classifying some of these things, and then we'll continue on here on Wednesday. So some quick definitions, types of quadratic forms here. So, first, I want to talk about positive definiteness. I want to talk about negative definiteness. And I want to talk about indefinite quadratic forms. Okay, so here's my definition. So a quadratic form, Q of x, is said to be positive definite if Q of x is greater than 0 for all x that are not 0. I have to include that because even when you have something that's like your quadratic form being the length squared or something, that even that is 0 for the 0 vector. It's negative definite if, well, based on this, you know exactly what I'm going to write here. And it is indefinite if it takes both positive and negative values. So if Q of x takes on both positive and negative values. Okay. All right, and two more things, and then that will set us up for what we want to say next about the relationship between these things and eigenvalues. So we have two more terms. Positive semi-definite is when you have the same thing except your inequality is not strict. Negative semi-definite, same thing. So negative semi-definite, defined in the same way. Okay. So this is just so that we can talk about these things using classifying language and have a nice way of completely characterizing what's going on. Okay. All right, so we'll continue on here next time. The main thing that I want to get into, like my main purpose of quadratic forms is going to be constrained optimization and then the singular value decomposition, the SVD. Those are going to be the two main applications. After we finish those, we'll see about, I'd promised previously that there'd be some fun stuff if we had extra lectures. So I'm going to talk about the Hadamard matrix conjecture for at least like one of those lectures. It'll only take one lecture. And then what else I do? Well, I'll come up with other fun stuff since we are at the cusp of finishing everything that is typically included in this course. Oh yeah, I'll do a bit on the Jordan canonical form, which isn't mentioned in the textbook, but like a good one and a half lectures will do you well on that. Do you have homework? You're gonna have one more homework that I will post. I'll post by Wednesday. If I don't post it tonight, it'll be posted by class time on Wednesday. You'll have one more. Yeah, you're gonna have one more homework that will cover basically all the stuff we've done since the last homework. It'll be roughly the same length. It won't be too long. So anyway. And since it will include some stuff that didn't make the cut on the last exam. So anyway, all right. So I think that's it for today. So as I said, I'll make an announcement, kind of clarifying some stuff about your MATLAB project. But other than that, I'll see you all on Wednesday. We're approaching the end. So that's that. So. See you all on Wednesday. I'll also announce soon when my next office hours are going to be. So it'll be sometime this week. I'll have office hours kind of vaguely for any lingering questions you have about anything in the material. So leading into the last weeks, you have any questions about stuff or you're confused about any concept we previously covered, then you can ask. So anyway, so I'll let you know when that's going to happen. And so you remember you have discussion tomorrow where they'll be going over your most recent exam. Other than that, like I said, I'll see you all on Wednesday, and we're getting close to the end, right? How many more lectures? Last day of class is not next Monday, but the Monday after. So I think that is 6 more lectures, right, after today. So 6 more lectures. It looks like lecture 39 is going to be the last one we do. So anyway, I will see you all later. I'll see you all on Wednesday.